Hello, and welcome back for another video. In this video, we're going to continue our study of polynomial functions by focusing more on the graphs. So it's very similar to what we did in the last section, but here we're focused mostly on graphs of polynomial functions, not the power functions. Let me share my screen with you and we'll review what the power functions look like because that determines the end behavior of the polynomials. But remember, the polynomials, they might have some kind of wiggle, some kind of hills and valleys in between, or it may just get sort of flattish, never truly flat, but flat-ish. Let me share my screen. In our first problem, you can see right here that we want to find the x-intercepts of this polynomial function. Now we know it's a polynomial function because 5x is a polynomial, x minus 6 is a polynomial, so x minus 6 to the whole number power 2 is a polynomial, and x minus 2 is a polynomial. And the product of polynomials is a polynomial, so it's a polynomial. Now we want to find the x-intercepts. These are the places where it crosses and touches the x-axis. Now this is not necessarily all the solutions that there are. Solutions is related to the degree. The number of solutions is equal to the degree of the polynomial equation. But if you find one solution more than once, it counts both times as a solution, and that's called multiplicity. Also, we may find solutions that have an I in them because we had a negative under the radical in the quadratic formula. Now, these ones with an I in them are solutions. They do count as one of the ones that correspond with the degree of the polynomial, but they do not act as x-intercepts. So x-intercepts have to be real numbers. They can't have any I parts. So let's look at this one. In this one, what we want to do, of course, is set each factor equal to 0 and solve. Remember that when you're looking for x-intercepts, that means that the y value, which is the function f of x, is equal to 0. So this is going to be replaced with a 0. That means that either 5x equals 0 or x minus 6 quantity squared equals 0 or x minus 2 equals 0. One of those three. Sorry about that. My dog has heard something. Now let's look at this one. 5x equals 0. Dividing by 5 still gives me x equals 0. What about this one? This sometimes messes students up because of the square, but keep in mind that this is just x minus 6 there 2 times. And that means that both of them are going to be the same. Now, it will count as 2 solutions, but both of the solutions are going to be the number 6. So keeping track, I've got 1 time I got the solution x equals 0, 2 times I got the solution x equals 6, and over here, I've got the solution that x equals 2, and that gives me 4. Now, I need to make sure, of course, that I've got all of them, so I check the degree of the polynomial. Take the highest degree term in each factor, so 5x times x being raised to the second power times another x. Well, that would give me 5x to the 4th. So I know it's got to look like this on the ends where it's going up on both sides, but it probably has some wiggling in the middle because I've got 4 different x-intercepts, which corresponds to the degree 4. So this one doesn't have any imaginary complex solutions. They're all real. Now let's take a look at the graph so you can see what it looks like and how these x-intercepts correspond. Now remember that x-intercepts should be entered as points and not single digits. So this should be 0, 0, the ordered pair, 6, 0 is there twice, and then 2, 0 is there once. Now what's going to happen when we have a multiplicity of 2? If you remember from the last video, an even multiplicity will cause it to bounce off of that x-intercept and stay on the same side. So we're expecting it to cross at the origin, cross at 2, 0, and bounce off of 6, 0. So let's sketch what we think it'll look like, and then we'll look at Desmos. So I know it's going to hit the origin and cross. It's going to hit the number 2 and cross, 3, 4, 5, and 6, and it's going to hit 6 and cross. I know 5x to the 4th has to open up on both ends like this, and I think in the middle, probably it wiggles some. Now, it is degree 4, so at most it has 3 turning points. Because they come in pairs, it's either 3 or it's 1. But because I have all of these x-intercepts, I think it's probably 3. So I know from the left it goes up, and I know from the right it goes up. It crosses at 0, so it's down. It crosses at 2, so it's up. And then it bounces off of 6 because it had even multiplicity. And that is basically what I think it should look like, something like this. Let's check it and see how well I did. Now I had to play with the scale quite a bit to get this one to show up and look like this. But this does in fact look very much like what I had before. So there are the x-intercepts, and if you click on the x-axis near the graph, then Desmos will offer up the points for you to click on. And you can see that these are the ones. And notice that it is bouncing off of 6, 0 because we had even multiplicity. So if it has multiplicity of 1, it crosses over kind of like a line, degree 1. And if it has even multiplicity, it bounces. What if it has cubic multiplicity? Well, it actually comes up and it approaches that one at a saddle point. So it comes up, narrows down to horizontal at that one x-intercept, and then goes up again. In other words, it looks like a cubic at that crossing. And we'll probably see one of those in just a minute. Let's now take a look at the next problem. In the next problem, we want to find the x-intercepts again, and we're given 3x to the 4th minus 6x cubed minus 9x squared. Now, it's much easier to find the x-intercepts in factored form, so we want to factor this. So the first thing we're going to do, again, is we're going to take out the greatest common factor first. That always makes it easier. Now, this one I can tell more easily what the degree is and what the leading coefficient is. It clearly, because of the 3x to the 4th, has to be degree 4 and leading coefficient of positive 3, which again means on the edges, it's got to be pointing up, and maybe it wiggles or it gets sort of flattish there in the middle. I don't know which one. Now, it could have 1 turning point, or it can have 3 turning points, right? So it either kind of does this, or it turns, and does this. Now, do I know it looks like a W? No, some of those dips could be lower or higher, whatever. So now I'm going to take out the greatest common factor. 3, -6, and -9 are all divisible by 3. I have x to the 4th, x to the 3rd, and x squared, so x squared is common. And when I divide them out, remember, if you have trouble with this, that you can always write it like this, and this will tell you exactly what's left behind. So if you have trouble factoring out the greatest common factor, remember that this is another way to figure that out. So this is going to give me 3x squared. The 3 divided by 3 cancels. X to the 4th over x squared is x squared. The 6 over 3 gives me a -2. X cubed divided by x squared is x. And then 9 divided by 3 is going to give me a -3, and the x squared is gone. Now, the fundamental theorem of algebra says all polynomials, not only polynomials, remember polynomials, real coefficients, and they have to be able to be written with all variables in the numerator and with whole number powers on those variables. They don't have to be that way, but you have to be able to write them that way. Now, the fundamental theorem of algebra says that when you have something like this, and it's a polynomial, then you can factor it down until it's either linear factors raised to powers, maybe, times quadratic factors that don't factor, and that's it. In other words, if it's a cubic and it's a polynomial, it's got a factor, right? So that sounds crazy, but that's the way it works. So this tells us it has to factor. Now that's true when it has the integer coefficients. So what we're looking at here is wondering whether or not this x squared minus 2x minus 3 factors, and indeed it does. I'm going to use trial and error. I know that these are going to be both x. I know 3 has to be 3 and 1, and that gives me 3x here and 1x here. I need it to be a -2, so I've got to attach the appropriate signs. So now I've got all factors. This one is quadratic, the 3x squared, the x minus 3 is linear, and x plus 1 is linear. Now to find the x-intercepts, I'm going to take each one and set it equal to 0. So I'm using the zero product property or zero factor property. It's called both. So this means 3x squared equals 0, or x minus 3 equals 0, or x plus 1 equals 0. Now, the 3x squared means that I actually get 0 as a solution 2 times. Because the degree is 2, I have to have 2 solutions, and x squared equals 0 means that I basically have plus or minus 0, which is still 0, but it counts as 2 solutions. So over here, I'm keeping track, that's 2. And then I've got x equal 3, that's 1 by itself, so it crosses here. And it should bounce off of this one. And then I have x equal -1, which shows up 1 time, so it should cross there. And that gives me all 4, which matches the degree of the polynomial, degree 4. Now we should write these intercepts as ordered pairs. So we have 0, 0, 3, 0, and -1, 0. Now let's put this one into Desmos and let's see if we can graph it. So our original problem was 3x to the 4th minus 6x cubed minus 9x squared. So 3, -6, -9. Okay. 3x to the 4th minus 6x cubed, I think it was, minus 9x squared. Okay, is that what it was? Let's make sure. 3, -6, -9. 3, -6, -9, 4, 3, 2. Okay, so we're going to turn this graph off. We're going to turn this graph on. And actually, this is not too bad. I can kind of see it here. Now, it's a little hard to tell if this is a saddle point or if this is actually a dip. Now, I know that because it is 4th degree, that there can be 3 turning places or 1 turning place. So either this is a saddle point or there is actually some up and down here. And oh, yeah, definitely. This comes down, it reaches a minimum down here somewhere, right there. And then it goes up again, and then it comes down again. So this one is very hard to find, but it's right there. So that's 1 turning point, and this is another turning point. And that must mean we have a 3rd turning point, which is, of course, right here. And again, if you get close to it, Desmos will offer it up as a grayed out dot for you to click on. Now, what are our x-intercepts? Well, I've got an x-intercept here at -1, and I've got one at 0, and then I've got one over here at 3. Did I do that right? Yes, 3. Okay, so when I'm looking at these, notice again, I'm going to click on the intercepts. Notice that when the solution was found, and it was only found once, that it crossed the x-intercept. And when it was found an even number of times, it bounced off of it. So you can see it's bouncing off the origin here, not by a lot, but it is definitely bouncing. Okay, let's take a look at the 3rd problem now. In the 3rd problem, we have a 4-term polynomial. Now it is x to the 3rd plus 2x squared minus 9x minus 18. Now we've got all integer coefficients, so we know this thing has to factor, and it has to be the product of linear factors, and at most a quadratic factor that won't factor further. And the last one, the quadratic factor, did factor, so they were all linear except for the x squared at the front. So what we want to do now is we want to try to factor this one. Because there are 4 terms, our technique is going to be to find a factor by grouping. Now, there is one other method called the rational root theorem, which we'll get to a little bit later on. But basically, when we look at this one right here, the only method that we have for a 4-term polynomial is to factor by grouping things. So we're going to group the first 2 and group the second 2. Now, does it have to be the first 2 and the second 2? No. In fact, there are some that will only factor if you group the first and the third and the second and the fourth, and some that will only factor if you group the first and the fourth and the second and the third together. So there's all different kinds. Now, when we look at this particular one, I pair them each and I take out what's common of each pair. So x cubed minus 2x squared has an x squared in common, and that leaves behind an x plus 2. And again, if you want to, you can always write this as x cubed over x squared plus 2x squared over x squared in parentheses with the x squared on the outside. What about the minus 9x minus 18? Well, if I do not get this x plus 2, then the method didn't work. So it's got to be x plus 2. Otherwise, I'm back to the drawing board. I have to try another pairing. So in this case, I need to not only take out the 9 that's common, I need to take out the negative because the sign in the middle of this expression x minus 2 or x plus 2 is positive. So I'm going to take out a negative 9, and that leaves behind x plus 2. And again, if you're not sure, take this out and write negative 9x over negative 9 minus 18 over negative 9. And you'll see that it does reduce to x plus 2. Now, what have I done? I've gone from 4 terms to 2 terms. And now I do it again, and I take out what's common between the 2 terms. So my 2 terms now are this one here and this one here. And they do have something in common. They have that x plus 2. This x plus 2 that you see right here, that's common. So to factor that out, I end up with x plus 2 times x squared minus 9. Now I've gone from a 3rd degree down to a linear factor, x plus 2, and a quadratic factor, x squared minus 9. I want to see if the quadratic factors further. If not, fundamental theorem of algebra would say I'm okay. This case, x squared minus 9 does factor, and so I get x plus 2, x minus 3, and x plus 3. Now, if I'm looking for x-intercepts, I set this equal to 0, and then I solve for the x-intercepts. So then I would have 0 equal to x plus 2 times x minus 3 times x plus 3. And then I can pretty much read them directly off. When they're linear factors, it's pretty straightforward. This is going to give you negative 2, x equal 3, and x equal negative 3, which are the ordered pairs negative 2, 0, 3, 0, and negative 3, 0. Now, I found 3 solutions that each showed up one time, and the degree of the polynomial was 3. So I know I have all the solutions, none of them are imaginary, and I have 3 x-intercepts. So when I graph this and look at it, I know that it's going to cross at negative 2 and cross at negative 3, and it's going to cross over here at 3 as well, right? Now, what does it look like in between? Well, it's degree 3 because of the x cubed term, and the leading coefficient is 1. So I know it's got to look like an uphill cubic, something like this. So when I'm doing that, it means it's got to be generally uphill. So it's got to come up, and then it's got to go up like that, because that's what a cubic looks like. That's going uphill. And then it crosses. So it's got to cross, it's got to wiggle. Oops, that was a bad wiggle. Okay, it crosses, comes down, crosses the x or y axis somewhere, and then it comes back up here. Now, if I want to be more precise at what it looks like, I could find the y-intercept. Now, the y-intercept's not difficult to get. All I need to do is let x be 0. I could either do that here, which would give me 2 times -3 times 3, which would be -18. Or I could do it up here, and then all the x terms drop out, and I get -18. So basically, this point right here is 0, -18, right? So this is what it's going to look like, the basic graph, right? Now let's go ahead and take a look at the next problem. This one is what we call quadratic in form, which means it's not really quadratic. It is a 3-term polynomial, so it's like a trinomial, and it factors like a quadratic does. It's not quadratic because the highest degree is 4, and so we know that it's gonna, and the leading coefficient is 3, so we know that it's gonna look like a cubic going up like this, and it either gets flat in the center or it wiggles, and it can wiggle 3 times or one turning point, 3 turning points or 1 turning point. So this is degree 4, leading coefficient of 3. So we know it's got to be uphill. That's our end behavior. And then we don't know how many turning points it's got. So let's go and see if we can find the x-intercepts. So what we're going to do on this one, and there's a couple ways of doing it, and I'll show you both. Right? Both methods work in all cases. It should be fine either way. The first thing you always do is take out the greatest common factor. In this case, 3 is a common factor, and it will help us by reducing the constants inside the parentheses. So this gives us x to the 4th minus 7x squared minus 18, I think. Yeah. All right. Now, there are 2 methods. One method is going to do what's called a u substitution. You find the middle variable part, and you let u be equal to that value. So you get u equals x squared. Now we want to know what u squared is. Well, u squared is x to the 4th, x squared squared. So I can rewrite this one as 3u squared minus 7u minus 18. And now I've turned it into something that is quadratic, and I know I can factor this one, or I could use the quadratic formula. And I'm looking for factors of 18 that have a difference, because the last sign is negative, a difference of 7. So it's going to be a -9 and a +2. So I've got 3 times u minus 9, u plus 2, always check. -9u plus 2u gives me -7u in the middle. And then I can set each one equal to 0, and I can back substitute. So now I'm going to have 3x squared minus 9, x squared plus 2. So this is my function. And again, I want to find out where the x-intercepts are. So I've gone back to x instead of u. So once I've factored it as far as I can go, I go back to x. Now I want to look at this and say, well, can I factor x squared minus 9? Well, yes, I can. So this becomes 3x plus 3, x minus 3. Can I factor x squared plus 2? No, I can't. It is what we call a prime polynomial. It doesn't factor any further. So this is what we mean by an irreducible quadratic. It does not break down into 2 linear factors multiplied together. So now, in order to solve this one, what I'm going to do next is I'm going to set each factor equal to 0. Now, obviously, 3 is not 0. That doesn't mean I've done anything wrong. It just doesn't give me a solution. And then I have x plus 3 equals 0. So I have x equal -3. Or I have x minus 3 equals 0. So I have x equal 3. Or I have x squared plus 2 equals 0. Now, when I move the 2 by subtracting it, I end up with x squared equal negative 2. And you're going to see in this case, because we have x squared, we have to have 2 solutions. That, however, when we do the square root, we're going to get a plus or minus the square root of a negative 2. So we get x equals plus or minus the square root of a negative 2. Now, the square root of a negative 2 is I square roots of 2. So this gives me plus or minus I square roots of 2. Now I've got one solution from x minus 3, one solution from x equal 3. I've got I square roots of 2 and negative I square roots of 2. So that's 4. What was our degree when we started? Yes, it was 4. I have all the solutions, all right? So these are all solutions. But the ones with I, these are solutions, but not x-intercepts, right? All right, but this is an x-intercept and a solution, and this is an x-intercept and a solution. So what is this going to look like? Well, I found the negative 3 one time and the 3 one time. So I know when I graph this that it's going to cross 1, 2, 3 here at negative 3 and over here at 3. And the leading coefficient was 3 and it's degree 4. So it's going to be up on both sides. So it's going to have to come up like this and up like this. And I either have 3 turning points or I have 1 turning point. But it never crosses the axis again, does it? No, it doesn't. So it never crosses the x-axis in between these. The only thing it can do is kind of come down, flatten out, and then go back up. That's all it can do. Now, if I want to know what the y-intercept is, this is the easiest way to find it, is in the non-factored form. And that would give you the constant term right there, which is negative 54. So I believe that this will cross down here at 0, negative 54. So let's put this one into Desmos and see how close we are. We have 3x to the 4th minus 21x squared minus 54. Okay, so we have 3x to the 4th minus 21x squared minus 54. Did I enter that correctly? Yes. Okay. All right. So let's turn off the blue one and let's take a look at the green. Oh, well, interesting. So I wasn't expecting that. I do actually have 3 turning points. I thought it was just going to come down and get flat, but it doesn't. It actually does turn 3 times. Now, how would I know that in a college algebra class? And the answer is you won't, all right? In order to know for sure that there are 3 turning points on this particular problem, we would have to use calculus. Calculus will enable us to pinpoint the exact values of these highs and lows, and we would be able to get the exact numbers, all right? So calculus is used to find relative maximums and minimums. So this one actually does wiggle. It just does all of its wiggling below the axis. So this one actually comes down, comes up, comes down, and then comes back up again. So it looks kind of like a W. All right. Let's take a look at this next one. This is problem number 5. Now on this one, I want you to do what we did previously. I want you to take out the greatest common factor first. In this case, it's an x to the 1st, and then factor it as if it were a quadratic in form. So you can make a u substitution where u is equal to x squared. So go ahead and do the work, pause the video, and then turn the video back on and we'll compare our answers. So how did you do? Let's compare our answers. So this one is clearly going to be degree 5 with a leading coefficient of 1. So we have degree 5 leading coefficient of 1 because the highest degree term is x to the 5th. Now, in order to factor this, I first took out the common factor of x, which left x to the fourth minus 5x squared plus 4. And I recognize that the middle term, if I squared it, would give me the first term. And so I let u be x squared and u squared be x to the fourth. That gave me u squared minus 5u plus 4. And when I factored it, I got u minus 4 and u minus 1. Now, I can't stay in u because the problem is in terms of x. So I've got to go back to x by back substituting that u is x squared. So this gives me x squared minus 4, x squared minus 1. And these, of course, factors the difference of two squares, which leads to 5 x-intercepts. Now, it was degree 5, so that's all the solutions. Every solution is an x-intercept, and each one shows up one time, which means it crosses over the x-axis at each of those values. And you can see that it's got to look something like this right here. Now, do I really know how high or how low these turning points are? No, I don't, right? I would need calculus to know that. I know in this case that there have to be 1, 2, 3, 4 turning points because there's no other way to go through the axis at each of those x-intercepts and draw it so that as x goes to negative infinity, the y value goes to negative infinity. And as x goes to positive infinity, the y value goes to positive infinity. Now, I said there was another way to do this. So let me go up here and I'll go ahead and write down a second way of doing these. So when you get to this step right here, another way of doing it is just to simply avoid the u substitution, but instead to recognize that x to the fourth is x squared squared. So you can just instead write it as x times and split up the x squared and the x squared. And then you know it's got to be minus 4 and minus 1 to give you a minus 5. And this sort of short circuits you straight to that step right there, right? Now, how else will this work? Notice that what's happening is when you square it, you double the power. So if I had an x to the third in the middle, I would need an x to the sixth as the highest power and a constant for the third term, all right? So it works anything like that. Okay, let's move on to our next problem, which is this one right here. It wants us to find the zeros and give the multiplicity for each. Now, it's given it to us in factored form. So what we have here is f of x equal to x minus 4 quantity cubed plus x plus 2 quantity squared. Now, what does that mean? Well, if I were to multiply this out and take that highest degree term inside each factor, I would have an x being raised to the third power times an x being raised to the second power. Remember, the constants have degree 0. And this would give me x cubed times x squared, which would give me x to the fifth. Remember, when the bases are the same, you add the powers. So this has to be a 5th degree polynomial, and the leading coefficient would be 1, which would be the coefficient that you see right there. So my degree is 5, and my leading coefficient is 1, which means it has to look something like this on the edges, right? It's got to be that uphill John Travolta Saturday Night Fever classic disco ball pose. All right, so when we're looking at this, what does multiplicity mean? Multiplicity means you got the same solution more than one time. So it has a multiplicity greater than 1. So when we write ours down here, if we're looking for the solutions, that means we're looking for the x-intercepts and also the solutions to the equation when y is 0. So we're replacing f of x with 0. Now, basically, this means I have x minus 4 times x minus 4 times x minus 4. I mean, it's there 3 times, right? So I get x equal 4, but I get it 1, 2, 3 times as a solution, all right? And that means it has multiplicity 3. That means it showed up as a solution 3 times, right? Now, what about the x plus 2? Well, the quantity is squared, so that means it was there 2 times, which means I have the solution x equal negative 2, and it showed up twice, so it has multiplicity 2. So I've got 5 solutions, 3 4s, and 2 -2s. Now, what is this going to do to our graph? Because this one is multiplicity 3, it's going to approach like a saddle point. Right? So now I'll draw you a picture of what a saddle point looks like. Right? So again, that's sort of like you're hiking. You think you're getting to the top of the mountain, but when you come over the crest, you realize that it just flattens out and then it goes up again. So a saddle point is where it comes up, flattens, and then goes up again. So the saddle point is right here. So it's going to cross the axis like that. Multiplicity 2 is even, so it's going to bounce off of that particular x-intercept and stay on the same side of the x-axis. So we have that 4 is going to cross like a saddle point. So we've got 1, 2, 3, 4. There's 5. So we know it's going to cross here like a saddle point, and we know it's going to bounce off of -2. And I sometimes will put a B for bounce just to remind myself. Now, the edges of it have to look like this because it is degree 5. So find the one furthest to the left, and it's got to be going down as x goes to -infinity, y goes down. And then this one has to come up here. Now, it has to bounce off of this one and then go down. And then it's going to have to cross this one like at a saddle point. So I actually want to redraw this one and then come up like that, right? Now, what is this value down here? I don't know, but I can find it, right? So the easiest thing to do to find that, of course, it's the y-intercept. So x is 0. So to find the y-intercept, I'm going to let x equal 0. So this would give me -4 cubed times 2 squared. Now, -4 cubed is a -64, and 2 squared is 4, so I get -256. So it's going to take a little bit of work to get this one on there, all right, to make it look right. So wherever it's crossing down here, it's going to be a lot lower. This isn't to scale. This will be at -256 on the y-axis. Let's go ahead and put this one into Desmos. This will be an interesting one so that you can see how I manipulate the graph in order to figure out sort of the grand scheme of the picture. All right, so I have x -4 cubed, x plus 2 squared. Right, so x -4 cubed, x -4 quantity cubed, and x plus 2 quantity squared. Oops, I lost my square. Squared. All right. So, oh, what happened to my x? All right. I don't know where that went. Okay, there we go. All right, now it's looking a lot better. Okay, so I can see the basic shape right here. And you can see that I've already adjusted the scale right here. So you can see it right here. And notice that it is approaching here at 4 like a saddle point. This is what I mean by saddle point. You're coming up, you think you're reaching the top of the mountain, and no, it flattens out and then it goes up again. All right, but this is a turning point and this is a turning point. All right, so ours in this case was degree 5. So we either have 4 turning points or 2 turning points or no turning points because they come in pairs and they count down towards either 0 or 1. So in this particular one, we basically have, and I'm going to scroll out so you can see the whole thing from a distance like that. We have 1, 2 turning points. A turning point means it really has to turn around and go the other way, not just flatten and then go off in the same direction again. That's saddle point. Now, if you were trying to graph this one yourself and you were using a 1-to-1 scale, that's what hitting that home does. You can see right here that I've got the intercepts, but I mean, this is way, way down there. So what I'm going to do is I'm going to come in here and I'm going to say, well, okay, it looks like I've got, pretty good at the top, but the bottom doesn't look good enough. So I'm going to start with 29. Now, why 29? Because then I don't have to do a lot of retyping. That's why. Well, that wasn't even close. I mean, yeah, it shifted it some, but I've still got, I can't see the bottom of that at all. All right, so let's try negative 69. So it's almost 70, negative 70. No, it's not big enough. So let's try 109. No, it's still not enough. Okay, maybe 150. You see how it's getting narrower here and getting closer to the bottom. But 150 wasn't enough. So the next time I'm going to go with 209. I'm close, but I'm not there. So the next time I go with increasing it by 50, and now I'm close enough that I can just use the scroll bar on my mouse and I can see the whole thing. All right. So hopefully this will help you in using Desmos and getting pictures. Let's now move on to problem number 7. Problem number 7 is exactly the way that we had the last one. So I want you to pause the video, work it out, and then turn the video back on and we'll compare our results. Okay, this one is a little tricky when you go to graph it in Desmos. This is actually one where it's almost impossible to get a good picture in Desmos, and I'll show you why in a second. So when we look at this one, the first thing I did was to find the degree of it by taking the highest degree term from each factor, x to the 4th times x quantity squared times x cubed, and that gave me x to the 9th with a leading coefficient of 1. Now, that means at most I have 8 turning points, but I could have 6, 4, 2, or none. When I set it equal to 0 and solved, I did get x-intercepts, and they had multiplicities of something. So 1, 0 is x equals 0, and it showed up as a solution 4 times. So I would put in multiplicity of 4. That accounts for 4 of the 9 solutions there are. Now, x minus 5 set equal to 0 gives me x equal 5, and that showed up as a solution 2 times. Now, both of those are even, so it's going to bounce off of both of those and go up. Now, when I looked at the last factor, x plus 8 to the 3rd power, that gave me x equal negative 8 with a power of 3, multiplicity of 3, which means that it's going to cross at that point like a saddle point. So when I look at it and I put this onto the graph, this is basically what I got. So it's going to bounce off of the origin and bounce off of 5, 0. And it's going to approach the point negative 8, 0 as a saddle point, but it's going to basically look like an uphill cubic, basically, from the left to the right. Now, when I tried to graph this one, I went up as high as 15,000, and I'm nowhere near to finding the top of this second bounce. I can't find this spot right here. Wherever this is, it's got to be like way up there, 50,000, 100,000, I don't know, but it's huge. And the problem is, the higher up I go, the more it tends to narrow things down a little bit, all right? So when I come over here and I look at the 8, you can see there is that sort of wiggle there. And as you scroll in, you can see, oh yeah, it is crossing there like a saddle point. And then we can scroll back out. And if you want to try, we can give it another shot. I can tell you that I've been working for a while. And I mean, this width right here tells me, I mean, I'm up at 10,000, so it's got to be like massively large. So I'll just keep scrolling until I think I can find it. 150, 200, 300, 400, maybe a million. I don't know. Let's try that. All right. So let's set this. Well, actually, let's scroll back in. I want to look at it very close to between negative 10 and 5. So I'm going to scroll until I get real close there. Okay, you can see this is really narrow because it goes up so high. So I'm going to set my maximum here to be a million. So right now I've got 13,978. Oh, that's too complicated. All right, so 1, 2, 3, 4, 5, 6. All right, have I gotten closer? Ah, I found one. Hallelujah. Okay, so here's one of them, somewhere around just above 50,000. but I still haven't found this other one. So I can go up higher still. I could make this 1.5 million by making that a 5. And I'm almost there. So I can tell it needs to go up a little bit higher, not a huge amount. So let's maybe make this 1.7 million. And now I've got it. All right. Now, what's the problem with that? Well, it's hard to see the rest of it, but you can still see the saddle point here, bounces off the origin, bounces off of 5, and it goes up from there. Now, it was quite difficult to get a decent picture on Desmos. We had to go up to almost 2 million, but we did it, right? Now, calculus is great because calculus will let us find these maximums here, relative maximums, without having to resort to a bunch of finagling on Desmos. Let's now turn our attention to the next problem. I want you to do the same thing on this one. This one, you will need to take out the greatest common factor first. There is a greatest common factor of x to the 4th. So remember to do that and find the x-intercepts, the solutions or roots or zeros, we call them the same thing, and their multiplicity. Let's compare notes. So on this particular one, it's already written out here, of course, in expanded form. So we know that the degree is 6 and the leading coefficient is 1, which means it's got to look like an x squared on the edges, all right, the end behavior. Now, because the degree is 6, the maximum number of turning points is 5, but there could also be 3 or just the 1. So we don't know what it's going to be. So we go ahead and factor this, taking out the greatest common factor of x to the 4th. It leaves a quadratic, which we then factor, and that gives us 3 x-intercepts. X equals 0, which showed up 2 times, so it bounces off of that point. X equals 6, which showed up once, so it crosses. And x equal -3, which showed up once, so it crosses. And this is sort of my rough estimate of what it looks like. Now, I have no idea how low these go, so let's look at Desmos and see how we did. Now, this one is a little bit easier to get all on here. I only had to go down to about 5,000, but it did take me a while. Notice that we do have turning points here. If I click close to where I think the bottom is, then Desmos will offer me the important points on the graph that I can click on right here. So you can see the x-intercept at 6, 0, the bounce x-intercept at 0, 0, and the crossing x-intercept at -3, 0. And you can tell that it turns 1, 2, 3 times. So it did not turn 5 times, it only turned 3 times, but that is one of our options. Let's take a look now at the next problem. This is very similar, but in this problem, we're asked to find the x-intercept and y-intercept. Then we're asked to give the end behavior. So on this particular one, remember what happens when you try to find the degree. So we're going to take the highest degree factor or term from each factor. So I've got -9x is one factor, x minus 1 is a factor, and x plus 1 is a factor, things separated by multiplication. So I have a -9x times x to the 1st times x to the 1st. And that gives me a -9x cubed, which means the degree of this is 3 and the leading coefficient is -9. So this is going to be like a downhill cubic. So it's going to be one of these guys coming down. Hopefully this looks right from your direction. I'm not sure because I don't know if it's mirroring or doing something else. So it should be coming generally downhill. So it's going to come down like this, and then it could wiggle or be a saddle point in the middle. Now it's degree 3, which means that we have either 2 turning places or no turning places. If it's a saddle point, there's no turning place, or there's 2. Now we can come over here and we can find the x-intercepts by setting each factor equal to 0. So y equals 0 equals -9x times x minus 1 times x plus 1. And this one is going to give me -9x equal to 0. So x equals 0, x is to the 1st. So it has a multiplicity of 1, showed up once. This is x minus 1 equal to 0, so I get x equal 1. It had x to the first, so it has multiplicity 1. And then I have x plus 1 equals 0, so x equal negative 1, and it has multiplicity 1. So when I add the multiplicities together, I get 3, which matches the degree. So I now have all the solutions. And when I look at this, I can write them as ordered pairs. So this is going to give me 0, 0, which is the origin. It's both an x and the y-intercept, so it's both. And then I've got 1, 0, and I've got negative 1, 0. So those are my x-intercepts, and my y-intercept, of course, since the origin is both, it's got to be the y-intercept. Remember, polynomials have precisely one y-intercept. They may or may not have x-intercepts. Now, we know that it's going to do like this on the edges. So as x goes to the right, it goes down. So the y value goes to negative infinity. So as x goes to positive infinity, y goes to negative infinity. And as x goes to negative infinity, that would be going to the left, then the y value goes to positive infinity. Right? And then we can take a look at what this one looks like. Let me put it into Desmos for you very quickly. This one is super easy to see. Just use the 1-to-1 scale by hitting on the home here. And you can tell that it's got 2 turning points. So we've got one here, we've got a turning point here, and it has the 3 x-intercepts that we found. They all had multiplicity 1, so they're all just direct crosses over the line. Now let's move on to the next problem, which is problem number 10. Now problem 10 is a little bit different. What it does is it gives us the graph, and it wants us to come up with the equation for it. Now, this can be kind of difficult sometimes, and that says of least degree, which means that actually there's probably more than one that has a similar graph. So we're going to look at this one, and we're going to see what we can do to figure it out. So the first thing we want to do is what we've been doing, which is finding the x-intercepts. Now, what we're going to have here is we have an x-intercept here, and we have an x-intercept here and an x-intercept here. So my x-intercepts are negative 2, 0, 1, 0, and 2, 0, right? Now, I know from where it came from that this means I had x equal negative 2, x equal 1, and x equal 2. And then I look at how it crossed the axis there. Each of these doesn't look like, none of them look like saddle points, so they weren't there 3 times. So they didn't bounce, so they look like they were there once. So that would be my guess, which means that this, if I back it up, gives me the factor x plus 2 equals 0. If I back this one up, I get the factor x minus 1 equals 0. And when I back this one up, I get x minus 2 equals 0. So again, I'm solving and having it equal 0. Then this must mean that I had an x plus 2, an x minus 1, and an x minus 2. Now you may think, hey, I'm done. No, you're not. All right, because we have to fix the y-intercept. This has a y-intercept right here at 0, 2. So I have to make sure that this comes out to be the number 2 when x is 0. And right now, I wouldn't get that. I would get 4. So what I have here is a constant at the front, which we'll call a. So this becomes y equals a times the quantities x plus 2, x minus 1, and x minus 2. Now, when I'm looking at this, what do I want to do? Well, the first thing that I want to do is I want to set the y-intercept. So I know when x is 0, y equals 2, and I got that off the graph. So I'm going to have 2 equal a times 2 times negative 1 times negative 2. So I let x be 0, and the y value's got to be 2. So on the left, I still have 2. On the right, I get 4a. which tells me that A has to be 2/4 or 1/2. And that gives me an equation. So I can use the equation 1/2 times x plus 2 times x minus 1 times x minus 2. Now, I don't know if it wants it multiplied out or not. I will do that example for you one time, and then we'll move on to the next problem. So this has to be 1/2. And then I'm going to write this one this way. But I'm going to multiply these guys together first because they're a conjugate pair, x plus 2 and x minus 2. And that's going to give me x squared minus 4, the difference of 2 squares. So this becomes 1/2 x squared minus 4 times x minus 1. And then I'm going to do the distributive property. So again, or you can think of it as FOIL. So you have x squared times x, which gives you x cubed. X squared times -1 is negative x squared. -4 times x is negative 4x. And -4 times -1 is positive 4. And then the whole thing is multiplied through by 1/2. So this would give me, in fully multiplied out form for my function of x, this would give me 1/2 x cubed minus 1/2 x squared minus 2x plus 2, right? Now, how could you be sure that this is the right one? Well, you can take this equation right here and you can go graph it and compare it to this graph right here. It should be identical. All right, let's go ahead and graph it and see what we get. So 1/2 minus 1/2 minus 2 plus 2. Did I enter that correctly? I don't think I did. 1/2 x cubed minus 1/2 x squared plus 2x. Oh, minus 2x plus 2. I got the signs backwards. Minus 2x plus 2. All right, let me turn this other one off. And I need to, well, it looks like it is a 1-to-1 scale. So it is definitely crossing here. Let's scroll this one down. Yeah, it looks pretty much the same. Right, so I know I've got the graph right. Let's take a look now at the next problem. In the next problem, you can see that we've got 2 turning points. So it's got to be at least degree 3. And it could be degree 5 or degree 7. And the leading coefficient's got to be positive. I don't know what it is, but it will be determined by the y-intercept. So what are my x-intercepts? Well, I've got this one here at -4, 0, and it crosses. So it looks like it's a solution 1 time. So that would give me a multiplicity of 1, and that would give me the factor x plus 4. And then I've got this one right here at 1, 0. But do you see how it bounces off the axis and stays on the upper side of the x-axis? That means that it must have an even multiplicity. Now, it could be 2, 4, 6, 8, but the minimum is 2. So I'm going to assume that I have x equal 1 with multiplicity of 2, the minimum possible. So this would mean I have x minus 1 quantity squared. So I've got these 2 multiplied together, and that's all the x-intercepts I've got. But I know it's got to be multiplied by some a, and this equals y. Now my y-intercept right here is 0, 1. So when x is 0, y has to be 1. So this is going to be a 1. This is going to be an a. So this would be a 4. And this would be a -1 squared. So I have to square first, order of operations. So that gives me 1 times 4, which is 4. So I have a equals 1/4. So my equation is going to be y equals 1/4 x plus 4 times x minus 1 quantity squared, right? and then you can multiply it out to get the fully multiplied out factor. And let's go ahead and check it over here and see if it would take it in factored form. So that was problem 11. Let's go down, see if it'll let us check it real fast. So problem 11, it doesn't say. So let's try 1/4 x plus 4 x minus 1 squared. So 1/4 times, oh, I've already forgotten. What was it? X plus 4 x minus 1, or x plus minus 1, x minus 1 quantity squared. All right, so x minus 1, yes, that's what I had. All right, so we don't know if it's going to give us the actual. So I'm going to have it give us both, and it liked it. All right, so I didn't have to multiply it out after all. So let's move on to the next problem, which is similar, but it doesn't have the graph. It just gives us the information, and it wants us to find an equation for a polynomial, the expression that has degree 3, has a 0 at 1, at -2, and at 2, and the y-intercept is 0, 8. So they're giving us the same information as in the last two problems, but they're writing it in words instead of doing it in graph form. So go ahead and pause the video, work this one out, then turn the video back on to compare. So once you get the hang of it, it's kind of fun, right? All right, so looking at this one, it's degree 3. So when I'm looking at degree 3, I can have at most 3 x-intercepts. I either have 1 or I have 3, because if I have an imaginary one, they come in pairs. So I've got to either have 1 x-intercept or all 3. And I've got 3, which means they each have to have a multiplicity of 1. So they have to cross at each one. And I have an y-intercept of 0, 8. So if the 0 or solution is 1, the factor is x minus 1. And if the solution is -2, the factor is x plus 2. And if the solution is 2, the factor is x minus 2. So I multiply these by a and set them equal to y. Now I know that when y is 8, x is 0. So these variable terms drop out, and I get 8 equals a times -1 times 2 times -2, which gives me 4a is 8 or a is 2. And that gives me this expression that you see right here. And let's go ahead and compare it. And I'll cheat, which you can't do, and you can see that that is indeed the solution. Now we can move on to the next problem, which is pretty much exactly the same. So go ahead and pause the video. Now you'll notice right here that these are given different multiplicities, which means that they're going to be a factor raised to a power that corresponds to the multiplicity. All right, pause the video and work it out. So again, following the same process, if the solution is -2, the 0 or root, then the factor is x plus 2. And if it has multiplicity 2, then the power is 2. If the solution root or 0 is 2, then the factor is x minus 2, and it has power 1 since it has multiplicity 1. If the solution root 0 is 3, then the factor is x minus 3, multiplicity 2 gives it a power of 2. So we get this expression that you see here in the center. Y equals a times quantity x plus 2 squared times x minus 2 times quantity x minus 3 squared. Now, we use the y-intercept to figure out what a is. When x is 0, y is -144. Notice that although the x drops out, the powers on each individual factor remain. And this gives us -144 equals -72. And when you double 72, you get 144. And so we get that a is equal to 2, which gives us this expression that you see here. Let's go ahead and check the answer to problem number 13, just to be sure we did it right. And you can see that that is indeed what we had. Now, I believe there are 1 or 2 more problems, these are word problems. So word problems are always more difficult. So if you want to pause it and go get a drink and then come back, that'd be just fine with me. You need a fresh brain for these. So this is a word problem. So we're going to read it through one time just to get a vague idea of what kinds of formulas might be important. All right. When we're looking at this one, we have a rectangle has a length of 16 units and a width of 6 units. Squares of x by x units are cut out of each corner, and then the sides are folded up to create an open box. Express the volume of the box as a polynomial function in terms of x. Okay, I'll be honest with you. I got rectangle and then cutting corners off, and I got lost after that. All right, so rectangle cutting corners off. But I know it's not a circle, it's not a triangle, and it doesn't have distance, rate, time, so I don't need any of those formulas. So let's go back to the beginning, and we're going to break it apart, words, 2 to 3 words at a time. So a rectangle. All right, so I'm going to draw a rectangle. Make sure when you draw a rectangle that you don't draw a square. Yes, a square is a rectangle, but not all rectangles are square. So draw one that's not square. That's usually better. Has a length. Okay, a length. Got it. Of 16 units. Okay, this is 16 from here to here. Okay, and a width of 6 units. Width of 6 units. Okay, so this is 6 from here to here. Squares of x by x units. Okay, now they're squares, so they're x by x, are cut out of each corner. Okay, well then I'm going to do this in another color. So I've got a square, and they're cut out of each of the corners, and they're all the same size. They're all x by x. So this is x, and this is x. And it's that way all the way around, right? So they're all x. Okay, got it. And then the sides, okay, are folded up. I'm not a very visual person, so I'm already getting a little lost, to create an open box. What's an open box? Okay, now before we go any further, what does help a lot of times is actually to create the model. You can just use a sheet of paper to do this. What I did was cardboard, because I found that for students who don't understand what's happening, it's almost impossible to solve the problem. So what I did was I took a rectangular piece of cardboard and I cut out squares from each corner. All right, so this distance and this distance are the same. And then it says fold the sides up. So you're going to fold these two together, and then you're going to fold these two together. And oh, that's what it means by an open box. It doesn't have a top, but it's got sides on it. Okay, so coming back out to the cutout part, and then folding the sides together again, you can see the box. Now let's go back out and let's figure out what each piece is. So when I fold it together, the height of the box is this distance right here, which when I fold it out, that's x, isn't it? That's x. So I'm talking about this length right here, but this is an x by x square. So the height of my open box has to be x. So I've got height equals x. Okay, now what else? So I'm looking at this thing, and when I fold it together, I've got the height. I need the width. Well, what's the width? The width is going to be this measure coming across here, all right, across the bottom. But that's also x. No. Or is it? Well, it depends, all right? I don't know that it's x. I know this is x, and I know this is x, but do I know that this side is x? I know the shape, the corner is x, but I don't know about this right here. So let's look at our shape and figure out what this would be. So when we fold it together, we're talking about this region right here. Maybe I should highlight it. It's this region right here. Well, what is that region? Well, that region right there is going to be, oops, I didn't quite get off my color. This is going to be 6 minus x from each corner. So that's 6 minus 2x. So my width is going to be 6 minus 2 x's, because this was an x and this was an x. And when I fold them up, then that makes the width of my box. So I've got 6 minus 2x. Well, then that means that to find the length, I need to do the same thing, because what is the length? It's whatever this is, and then I cut off x's from each side. Well, originally it was 16 long from side to side, so it's got to be 16 minus 2x. So that would be this region that we've got right here. And when I look at that, this has to be 16 minus 2x. So that's my length. 16 minus 2x. So how do you find the volume of a box? Well, length times width times height. So now that we've written everything down, we can express the volume of the box. So we can write that the volume is equal to length times width times height, or whatever order you want to multiply in. I'm going to write x, 6 minus 2x, and 16 minus 2x. And that represents a polynomial function, because each of those factors is a polynomial. So it's a polynomial function. And we can go ahead and check. I don't know if this one they would have multiplied them out. I doubt it. Nope. 16 minus 2x, 6 minus 2x, and x. So we know that we've got it right. All right, let's take a look at our last problem. A right circular cone has a radius of 2x plus 3 and a height 5 units less than its radius. Express the volume of the cone as a polynomial function. The volume of the cone is 1/3 pi r squared h for radius r and height h, inner pi is pi. Okay. All right. So now we're going to have to figure out what we need to write down and what kinds of things we need to have. So we have a right circular cone. Well, again, it helps to know what you're looking at. This is basically an ice cream cone, all right? A normal cone shape, all right, or a traffic cone. So a right circular cone. So let's write, let me draw one here, right? Or I could do it in this orientation, like this, right? So here's the center of the bottom. So the height comes down, forms a right angle. So this would be the height going to the bottom. And then the radius would come out here like this, right? So we know that our volume, we're given the formula 1/3 pi r squared h, all right? So we need to write the volume of the cone, expressing it in some kind of polynomial fraction. So let's go back to the beginning and let's figure out what it says. A right circular cone. Now, the word right means that this at the bottom, where the height comes down to the base, is a right angle. It's not tilted sideways, right? It's not a squashed cone, not slanted cone. Circular means that the base is a circle as opposed to like a square or something, which wouldn't be a cone at all. It'd be a pyramid. So in this case, we have a right circular cone, has a radius of 2x plus 3, right? So r equals 2x plus 3, and a height, got it, 5 units less than its radius. Okay, now we need to interpret the words less than. Less than reverses the order. So when it says 5 units less than, what it means is that the height is equal to something minus 5. 5 less than means minus 5. And it's less than its radius, so this is r. Now r is 2x plus 3, so I should be able to substitute 2x plus 3, and then I still have minus 5. And that tells me that h, when I combine the 3 and the negative 5, I get that h is equal to 2x minus 2. Now I'm ready to put it all together. So I've got my volume equals 1/3 pi times 2x plus 3, that's the radius, squared, times the height, which is 2x minus 2. And that should give us the volume of the cone in terms of x. And we can come over here, and I can cheat and get the answer for you very quickly. 1/3 pi, 2x plus 3 squared is the radius, 2x minus 2 is the height. So I hope that this has helped you with your homework, and I hope you'll join me for the next video in this series.